All right, guys. So I want to start off by just saying a big thank you for all of your help with this. This is a transition for a lot of us, so please be patient. We're going to do the absolute best we can to make sure that you guys get the most quality educational experience that you can. So this is the review, just like what we would do in class. The only difference with this is I'm just going to do this in an audio and a video clip. A couple things to keep in mind with that. This is optional, so don't feel like you actually have to go through this if you fully understand things. This is just another way for me to communicate with you some important information. So we're going to start off by just talking a little bit about equilibrium itself. Now keep in mind, we did kind of lie to you by saying that all chemical reactions go to completion. They actually don't. So not all reactions go to completion. Not all of your reactants are going to be converted into products, okay? It's just the nature of chemical reactions themselves. You're going to have some reactants left over from that reaction. Now, it appears as we go through the reaction that the reaction stops. We get a certain amount of product from our reaction and we're done, and that's actually not the case with equilibrium. Equilibrium, when something is at equilibrium, it means that the rates going from reactant to product and product to reactant are equal, okay? So what that means is that my reactants are forming products, but my products are also forming reactants, and they're doing that at the same rate, which is why it appears that the reaction has stopped. The reaction doesn't stop. You're in equilibrium. It's also known as dynamic equilibrium because it's still moving. We have just molecules going from reactant to product, and product back to reactant. They're just happening at the exact same rate. Okay, and we can do math with this as well. We can figure out and solve for what's called the equilibrium constant. And the equilibrium constant actually tells you whether I'm going to get a lot of product from my reaction or very little product from my reaction. Whether equilibrium lies closer to my reactants, which means that I'm going to get very little product, or closer to my products, which means that the reaction essentially goes to completion. So I just listed a couple of them here. These are all different chemical reactions, and you can see the equilibrium constant can be a very, very small number. But also notice that exponent. So don't be alarmed if you see really large exponents as you go through and calculate these. Okay? So just kind of moving down here, talk a little bit about rates of reaction and concentration. So let's say we start off with a chemical reaction. Okay, let's do the one that we have listed here. So we've got lots of H2 and lots of I2. And we want to form HI from that. Okay. Now, as we go through this reaction, we're going to start off with a lot of reactant, right? Because we start off with our reactants and no product. So as you see here, as on the graph here, as the reaction happens, the forward rate of reaction is actually quite high. And that makes sense because we have nothing but reactant. We have no product. Okay. Do keep in mind that this is a reversible reaction, meaning that we can go from reactants to products as well as products back to reactants. As the reaction goes forward, the rate of the reaction, notice the rate actually decreases. The reason for that is that we have less reactant. We have less reactants that are able to react with one another to form product. But notice that the reverse reaction increases, and that makes sense as well because as we get more product, that means that there's more product that can react to form back to reactants. Okay? Now eventually, the forward reaction decreases and the reverse reaction increases to where we get a state of equilibrium. Okay, and that means that the forward and reverse reaction are the rate of the forward reaction and the rate of the reverse reaction are the same. Okay, now one thing to keep in mind here: this does not mean the concentrations are equal. Okay, does not mean that the concentrations are equal. Okay, we can have a reaction that's in equilibrium where I have tons more products than reactants, and vice versa, a lot more reactants than products. You could still have something in equilibrium. Okay, but do keep in mind, when we talk about equilibrium, it's only focusing on the rates of reaction. Okay, now we can determine whether equilibrium lies more in my reactants or more in my products, meaning I get more reactant or more product from the reaction. Okay, and we'll look at that here in just a moment. So again, we can do some math with this to be able to solve for the equilibrium constant here. You have your basic chemical reaction here. You have your double-sided arrow. A plus B yields C and D. And then you have lowercase a and b that represent your coefficients of your balanced chemical equation. In order to write this, you basically just take its products over reactants. So concentration of products, we did talk about that before, over concentration of reactants. And the coefficients actually become exponents here. So D, A, whatever. They become your coefficients that go at the top. So we can write equilibrium expressions relatively easily. So let's write the equilibrium expression for the following here. You've got all this information. All right. And remember, it's just product over reactant. So we're going to say K. All right. And we're going to put our concentration of our product over reactant. Okay. And then literally you can plug numbers in. So if I had the concentrations for these, I could plug in and solve. All right. Pretty straightforward on how to go through and do that. We'll talk a little more about this in just a second. So what does K actually mean? Like, K is a constant value. That value has to have meaning. Well, depending on whether K is a very big number or a very small number, that actually tells you which direction the reaction is going to go. Okay? By that I mean, where does equilibrium lie? Does equilibrium lie closer to my product or closer to my reactant? And so we've got some really good information here. But what I really want us to focus on is just K. If K is greater than 1, then I get more product. And if K is less than 1, I get more reactant. Okay? And the magnitude of K actually plays a really huge role in determining whether we go really, really far to our product. So if K is somewhere between times 10 to the negative third and times 10 to the third, then you're going to have significant amounts of reactant product. Okay? It doesn't mean that it's going to be the same on both sides. That would be if K is equal to 1. But anywhere in the times 10 to the negative third to times 10 to the third, you're going to have significant amounts of both. If K is very, very large, meaning greater than times 10 to the third, then I'm basically going to have all product, no reactant. Equilibrium lies very, very far to the right-hand side here. And so if we think about this kind of like, this is reactant and this is product. Okay, and this is where K is 1. If my K value is really, really large over here, that means I'm going to get almost all product and no reactant. And if K is very, very, very small, okay, then I'm just going to have most reactant and no product as a part of that. Okay, so just kind of keep in mind that the magnitude of K tells you a lot about whether we're going to get a lot of reactant or a lot of product. Okay, so I can solve for K. Cool. Give the equilibrium system of this here. So there's my equation here, equilibrium, because you have that double-sided arrow. You're given concentrations, you can solve for K. So the first thing we need to do is write out our equilibrium expression. So K, concentration of PCl3 over Cl2. I'm sorry, times Cl2 over PCl5. Okay. Now, again, if we had coefficients, we'd make them exponents. We don't have to do that. So it's pretty straightforward here. And then we're just going to solve for K. So we're just going to plug numbers in. So K is equal to, we got 0.40 times 0.40 all over 0.32. All right, and then we just simply plug that into our calculator and solve. K is equal to 0.5. And so I could ask you some other questions about this as well. If K is 0.5, then is equilibrium going to lie more towards your reactant and more towards your product? Well, if we take a look at kind of the line up here, K is 0.5, so it's going to be somewhere over here. So that tells us that equilibrium lies close to my reactant. The very last bit of this first part of the unit is down here, and that is heterogeneous equilibrium. So heterogeneous basically just means that we have mixed phases. And when we have mixed phases, a couple things to keep in mind here, we are never going to include liquids or solids in my equilibrium expression. Never, ever, ever include those in my expression because the concentration of those don't change regardless of the reaction. You know, if we have water, water is a liquid. if water evaporates, the concentration of it doesn't change in a chemical reaction. It's still 100% water. So to write heterogeneous equilibrium, it's actually all pretty straightforward here. So let's do let's do D and G. Okay, so we'll do D here. So K is products over reactants. So we've got SO2 here, which is a gas. But we have two solids. We never include those in our expression, so it's just SO2. And if there were a coefficient, you'd still make it an exponent, but we don't have to worry about that. All right, and then let's do G, and we'll call it a day. So down here we have K. Remember, it's products over reactants, so H2O. Oh, no, we're not going to use H2O. You know why we're not going to use H2O? I still can't use my iPad. We're not going to use H2O because it's a liquid, right? So we don't include liquids, and we don't include solids. So this is just going to be CO2 over concentration of O2, and we're going to square that, and CH4. Okay, and then again, if I were to ask you numbers, you could plug in and solve, and then if I gave you a value for K and concentrations, you'd be able to solve for that as well. All right, that's the video review for today. Hopefully you guys got a lot out of it, and if you guys have questions, you can always just let me know. Have a great day, guys. Bye-bye.